Hi again. In this video, we're going to do another example of a theoretical hypothesis test. And we're going to go through all of our steps. So let's go. Let's see what this one says. In 2014, the official poverty rate was 14.8% in the U.S. A city official wants to test if their county has a different poverty rate than the rest of the U.S. In a random sample of 2,000 county residents, 13.3% were below the poverty level. Is this enough evidence to show that the county's rate is significantly different than the national rate? Okay, so county, here's what we're testing. Is this enough evidence to show that the county's rate is significantly different than the national rate? Okay, do you know what type of test that is? Left tail, right tail, or two tail? And then let's also see what else we're given. We have a p hat. Now we have two different percentages. So this is one where we have a null parameter and a sample statistic, p hat, right? So this is the county one. This is the one they want to test. The county officials want to test if it's significantly different than the national rate. Okay, so this 14.8, we'll put it in decimal form. That's our P0 or P0. And the 13.3 is our P hat. So it's important to distinguish those two. And then we know our N is 2,000. Okay. Okay, well, let's go out with step A, and that's writing our hypotheses. H0 is P is equal to 0.148. Okay, so that's saying the poverty rate in the county is the same as the official or the whole U.S. poverty rate. Okay, and then the null, significantly different. If you said two-tail test, you're right. The alternate is that, sorry, I think I may have said null. The alternate is that the P is not equal to 0.148, and this is a two-tail test. Okay, so those are our hypotheses, and then we can write our conditions, and we'll do the quick version, because these questions are so long anyways. But remember, read the directions if you're asked to write them out, you know, in a full discussion. Okay, so independence. So we would need all the people sampled to be independent of each other. In terms of poverty or income level. See, I just can't do the short version. Random sample. And the reason is I think it just helps by making it really concrete. We would need a random sample, and it does say that. Okay, so now this large population could get interesting, right? Large population, or you could just write population must be greater than or equal to, I'm going to add a 0 onto this, so that's 20,000. Okay, since we would sample without replacement, we wouldn't ask the same person twice. We need to make sure this is the small bag of M&Ms versus large box of M&Ms. If we took 2,000 out, we need to make sure that it's a big enough box of M&Ms that it doesn't affect the probabilities. So we need at least 20,000 residents in the county. Otherwise, we couldn't use that large of a sample, and we wouldn't have independence. Okay, and then I'm going to check success failure. Okay, and remember we use our P0 for that, our null. So N 2,000, not too worried about 2,000, but this 0.148 is on the small side, right? And then our NQ0 would be 2,000 times 1 minus 0.148. So let's see what both of those are. 2,000 times 0.148 is 296. So yeah, plenty large of a sample size. And 2,000 parentheses 1 minus 0.148 is 1704. Now you might notice if you get one of them and it's a whole number, the other one, these have to add up to 2,000, right? Because P naught and Q naught add up to 1 or 100%. So that's a little trick you could use. Like if, let's say one came out to 200, let's say it was 1,000. If one came out to 200, the other would have to be 800. So just little tricks if you're interested. And sometimes it helps as a double check. If I was way off, these wouldn't add up to 2,000. Okay, so we are good. These are both greater than or equal to 10, so we're good, as long as that population is 20,000 or more in this county. Okay, so next is I'm looking at C, calculate our test statistic. Okay, so I'm going to write Z equals, and here's our formula. I'll write it out again. P hat minus P null, or P naught, over square root P naught Q naught over N. P hat minus P naught over square root P naught Q naught over N. Okay, let me move this up. Okay, so our P hat is the 0.133. We haven't used that yet, right? Because remember, ideally we're setting up our conditions and our hypotheses before we take any data. It's a little unusual in a stats class because we're doing everything at the same time. But really we would need to set up our conditions, make sure we get our numbers in a good way that we're going to be able to use the normal model, and set up our hypotheses in advance. So all that's in advance. So now we just collected our data. We got 0.133 minus 0.148 divided by the square root of, and we're using our null, so 0.148 parentheses 1 minus 0.148 all over 2,000. Okay, I'm curious to see how many standard deviations away this is. So let's get the calculator out here. 0.133 minus 0.148. I'm going to hit enter. Okay, it's negative, so it's going to be in the left tail, which makes sense because it's the observed rate is less, so that means it should end up in the left tail. Okay, divided by square root 0.148 parenthesis 1 minus 0.148 close parenthesis divided by 2,000. Okay, I get negative 1.8891. Okay, so it's negative, it's in the left tail. It's a two-tail. So in a two-tail test, depending on which side your observed statistic, your observed result is on, could end up on either side, right? So when we put this into Staplet, we need to make sure we put this in the left tail. Okay. So we got our test statistic, our z-score. I don't know. This is not 2 standard deviations away, right? So I'm not quite sure. Is this going to be significant or not? So our p-value, we're going to find the probability that z is less than or equal to negative 1.8891. Okay, now here's where I'm going to show you, and I think we've done a two-tail test before, but we've done it on simulations. So theoretically, if we just use the left tail, we need to multiply this by 2, right, for both tails. Or I'm going to show you on Staplet, you can use, I think it's outside, so I'm going to go there first. Okay, so here's our blank normal distribution. Calculate an area is what we're doing because a p-value is a probability. I'm going to put in 0, 1, plot distribution. Okay, let's say I'm going to just do the left version and multiply by 2. So I would go to the left of a value, put in negative 1.8891 because that's the z-score. Hit enter or calculate area. Okay, so it shows you it's on the left tail and we get 0.0294. Okay, so I'm going to write that down. Equals 0.0294. But that's just one tail. So then I'm going to multiply that by 2. .0294 times 2 is 0.0588. Okay, now let's say I want to use the other way. If you just want one way, that's fine. Just pick one way. But remember I mentioned before there was this outside. And outside is both tails. It doesn't have to be symmetric. It's giving us a different left option for left boundary and right boundary. So for this one I would put, the RZ score was negative. So I'm going to put the negative 1.8891 in the left boundary. And then it is symmetric. So I'm going to put 1.8891 in the right boundary. And now it shows me both tails on the graph, okay? So then I don't have to multiply it by 2. It's multiplying by 2 for me, okay? So either way, you can do it either way. If you draw a two-tail or use a screenshot of this two-tail test and you've got your p-value, this is 0.0589, that's great. Or if you show one tail multiplying by 2, that's fine as well, okay? The main thing is that depending on the sign of your z-score, if you came out negative, remember the negative always goes in the left tail, and then the positive goes in the right tail. So if we had to come out with a positive z-score, we would have to put that in the right boundary. And same thing here, we would have to put that in the right, to the right of a value as well. Okay, so the sign does matter. If you get it in the wrong one, it's not going to come out right. And so if your p-value is ever over half, or you're seeing like most of this graph shaded, then double check. Then you're probably putting it in the wrong side. Okay, our p-values are always going towards the tail, so they should always be like at most like 20%, like 0.20 at most. You would never see anything, rarely see anything larger than that, okay? Okay, so you can do it either way. You can either do outside a region. Let me go back to the notes. So you can either multiply by 2 for both tails or use outside a region. Okay, and I'll draw a little sketch here. 0 in the middle, 1, 2, 3, 1, 2, 3. And this was just under 2 standard deviations away. 1, 2. So my drawing is not very symmetric. It's kind of a problem when I'm trying to show that it's symmetric on both tails. I'm just going to keep fudging it till it's a little more symmetric. Okay, but what I can show you is this is 0.0294, and this tail is also 0.0294. So both tails have the same probability. When we multiply by 2, we get 0.588, or you may have noticed on here it was 0.589. So that was slightly higher. It's just round off error. So either one would be acceptable. This was from outside. Okay, just a little note there. Okay, so let's do our conclusion now. So we've got our p-value. We need to compare it with alpha. So how does this compare? Either these are going to be the same result, right? So 0.0588, I'll just stick with that one. That is greater than 0.05, right? So this is not significant. Okay, so we are not going to reject the null. Okay, we don't have significant evidence. Okay, so let's write our conclusion. ABC, so this was D, compare. So this was D if I'm writing my steps out, and then this is E. State the conclusion in context. So with a p-value of 0.0588, we fail to reject the null, and we do not have evidence that the county, whether the county poverty rate is different or significantly different from the U.S. poverty rate. Notice if it was a one-tail test, it would have been significant. So that is always something to consider when you're setting up a test. Okay, now I do want to do two things. I want to see what our p-value would be with a randomization distribution. Okay, so let's do that really quick. And then I also want to compare the 95% confidence interval. So I'm going to go to stat key for the randomization test. So this is good review. Test for a single proportion. And we need to put in our null and then put in our p-hat. So our null is 0.148. Okay, I've got that. And then we're going to edit data. We're not using any data that's already in there. Now I do need to know a count, and I wasn't given that. So let's calculate this on the side real quick. So this is for, I'm just going to put a note that we're doing the randomization. Over here, we need to know what 2,000 times 0.133 is. We know how many people that is. 266. Okay, actually came out as a whole number for once. Okay, so then that's telling me 266 out of 2,000. Oh, probably because it was 2,000. 266 out of 2,000. So let's go back there. Our count is 266 out of 2,000. And that we have to put in advance just because that sample size, remember when we do sample to sample variation, we always need the same sample size. It's specific to that sample size. So that's why we have to have that in advance. Okay, so this is our randomization distribution. So we're assuming the null is true. So this should be centered around 0.148. I generate 1,000 samples and 2,000 samples. Okay. And then do you remember how we got our p-value? This is a two-tail test. So we're going to click on two-tail. And then remember, it always comes up with 95 in the middle. So we've got 0.133 and 164 at the bottom. We need to put in our observed statistic. Now, it just so happens that it's already in there. So 0.133 just happens to be right on the boundary. So it looks like, yeah, so it's actually 0.025 plus 0.025. So this comes up right exactly at 5%. So this is like right on the border. So I'm going to write this on the notes just to compare. So this was our p-hat. And our p-value equals exactly, I'll put a little box around this on the side so you know that that was a separate thing. That's from our randomization. Our p-value is 0.05. Okay, so in that method, we would, I'd have to look and remind myself which way it goes, but it's right on the border, right? Okay, so now remember, this is different. So if I restart this, if I reset the plot, it keeps my information and I do 2000 again and 2-tail, I could get slightly different results, right? So now I'm getting 0.132, so that would be a little over. If I change this to 0.133, it's going to be just a little over 5. We get 0.037 in the tails. And if I add that together, multiply by 2, 0.037 times 2. Oh wow, that's actually coming out a lot higher than 0.05. So this is right. You know, one simulation could reject, one could not reject. So this is probably one where further study would be needed, right? Especially if you're right, it's really borderline. Okay, so let's go back to the notes. So I got a p-value of 0.05 that one time, but then I also got 0.074. So similar, but can vary, right? And we got 0.0588 between those two. Okay, so similar but different, similar results but slightly different, which is what we expect from empirical results. Okay, so now let's do our confidence interval and see what happens there. So I'm going to write out my formula, p hat plus or minus z star times the square root p hat q hat over n. Okay, now on the interval, remember we do everything with p hat because that's all the information we know is p hat and n. Okay, so this is going to be 0.133 plus or minus, and we were using the 5% rate, so we're going to use 95% confidence, 1.96 square root 0.133 times 1 minus 0.133 all over 2,000. Okay, so I'm going to rewrite my 0.133 plus or minus and calculate the margin of error all at once. 1.96 times the square root, 0.133 parenthesis 1 minus 0.133, close parenthesis, divided by 2,000. Okay, 0.0148. Okay, pretty narrow, right? 1.4% margin of error, 1.5 margin of error, because we have this big sample size. Okay, let's find out our interval. Let's go ahead and do the plus or minus part. 0.133 minus 0.0148, enter. Oops, I got a negative, so I did something wrong. 0.133 minus 0.0148. There we go, that looks better. And 0.133 plus 0.0148. Okay, so I'm getting 0.1182 to 0.1478. 1182 to 0.1478. Okay, now we need to see where the null value falls in that, right? Remember the null value was 0.148. Wow. 0.1478 would round. So I'm going to say put it like right on the edge here, 0.1480. If I add a 0, it's just right on the edge of the confidence interval. It's slightly out. Okay, so it's slightly out. So if the null value falls outside, that's evidence against the null. If the null value falls inside, that supports the null. So because we didn't reject, I would kind of think that it might be inside the interval, but it's just barely outside. So these slightly disagree in this case. But we've also seen that from our simulation, we could have gotten two different answers, right? So this one is definitely borderline. So I would say on this one, the null value falls barely outside. Out. Got an extra I in there. I'll get rid of that. Barely outside the interval. So the two methods disagree. In this case. Okay, so this would be a good opportunity or good time to do another study. Okay, so I'm going to say further study. Further study is needed, okay? So it's just outside. That's really supports. So since it's outside, we would reject the null, right? So it's outside. That one supports rejecting the null, whereas with the hypothesis test, we did not reject the null. Okay, well, there's another example, and I'll see you in the next video.